Okay, so let's get started. Hello, everyone, and welcome to today's seminars. We've been doing this now for throughout the semester, every 2 weeks, and I'm very happy to welcome Jens Mahlmann from Dartmouth College. The title of today's talk is Extreme Plasma Processes Around Compact Objects. Jens is an assistant professor. He just started at the Department of Physics and Astronomy at Dartmouth College, and he specializes in high-energy astrophysics. His research focuses on plasma processes in magnetized environments, particularly around neutron stars and black holes. And he uses advanced computer simulations and theoretical frameworks to investigate how electromagnetic energy in stellar magnetospheres transforms into observable signals. So Jens, just as a bit of background, got his PhD from the University of Valencia. He was an undergraduate at the University of Hanover, and since then he has held research positions at Princeton University, at Flatiron, and Columbia University. So I've known about his work for some time now. He has had vast experience in mentoring students throughout his career, which is a really impressive record. And at Dartmouth, he is currently establishing the Extreme Plasmas Around Compact Objects group. And he's looking forward to welcoming his first students. So let's welcome Jens and let's get started. The format of the talk, as you know, is about 50 minutes with questions. It's up to you, Jens. If you want people to interrupt you during the talk, that's possible. Or we can hold the questions for the end. And then we just, in this series, we also kind of reserve the last 30 minutes for any general discussions. It's sort of very informal, any questions that come up. And again, I will be recording this for our YouTube archives. And so please mute yourself if you're not speaking. Thanks again. So please get started.
Yeah, thank you so much, Reshmi, for that kind introduction, also for inviting me and for running this series, which I've been enjoying for the last weeks, actually. I will start by sharing my screen so you can see my presentation now, I hope. Yeah, so I'm at Dartmouth College right now. So it's in Hanover, New Hampshire. I'm full circle after starting off in Hanover, Germany with my first semester of physics. I want to tell you a bit about these simulations mainly that we've done to explain some of the extreme plasma around neutron stars and magnetars will be the focus of today. A lot of this work has actually been done at Columbia while I was there just before coming here with Andre, Lorenzo, who are there. Also a lot of work with Sasha Filipov in Maryland and other collaborators that I mention here. Yeah, please interrupt me whenever possible during the talk. I'll be happy to deviate from my slides and follow what you're interested in your questions. So the compact objects that I want to discuss today are neutron stars. There are two big categories that I'm interested in. The first one is this main category of pulsars. Pulsars, are spinning rapidly. They have strong magnetic fields. They're extremely good clocks because they have this radio emission that they send towards us. They are steady emitters. And today we think that they have an abundant plasma supplied by pair production that is governed by QED processes in the stronger magnetic fields, for example, around the polar region, but also in other parts of this magnetosphere, as people will study. The second part of the talk will be about magnetars. I'll explain more about them in a bit. What I want to first focus on is if you don't have just one of these pulsars, but you have two of them, you put two of them together. In this talk, I will focus on close binaries that are just before mergers. There's also other scenarios that you could think of where you would have not just one neutron star, but a neutron star and a companion. And then this neutron star companion wind actually affects the magnetosphere of the star you're interested in. And you can study all sorts of interactions between the wind and the neutron star magnetosphere. Or actually, it's very interesting. So I'm in a department now where there's a lot of space and near-Earth plasma sciences, where you also have dependencies of, for example, Kelvin-Helmholtz instability on the inclination of the Earth magnetic field. And similar things you can study in these kind of magnetospheric wind interactions that has been done last year by Jorge Cortés and Yi-Tze Chong. You can read their papers on that. Today, I want to focus on this problem of close binaries. They're extremely important, of course. So we have observed them, people have observed them in gravitational waves. They're emitters of an abundant zoo of signals that can happen after their merger. So we have a long catalog of both observations and theory that we can associate with it. What's interesting is that it's much harder to come up with models that could explain pre-merger signals that are not commonly seen. So such pre-merger signals would, of course, be great because then you would know where to pinpoint your observational power when the actual merger happens. And several people actually have looked into how electromagnetic radiation could be created in this phase of the merger process. One notable work, or several notable works, were done by Elias Most. So they have actually looked at. Sorry, I have to move. I have to move your faces around my screen. So they actually have looked at magnetic fields of here anti-aligned in-spiraling neutron stars. And what they found is that if you wind these magnetic fields during the spiral, you can create these outflows and eruptions, flare-like eruptions, almost solar mass ejection-like eruptions that could then provide a lot of energy actually for electromagnetic radiation like X-rays, which I will talk about in a bit. And they also postulated actually that this could be interesting for fast radio bursts, which is also something interesting. So on top of the reading that I kind of shared with you on recent fast radio burst associations with neutron stars, there has actually been a lot of different signals that are not necessarily associated with neutron stars, but they have very interesting pathology. So fast radio bursts are these millisecond duration pulses, and they come to us from sometimes very far distances. Because they interact with the free electrons in the universe, they have dispersive properties that kind of tell a story of their cosmic journey. And some of them, after they have been de-dispersed and cleaned of all these propagation effects, have interesting patterns in them, like this one, which has a kind of period in it. And the question always in these signals, we have so many of them, so many we can't explain, could be that if, for example, this periodicity is explained by a periodic process, like a neutron star binary system. I'm not saying that it is, but it's this kind of speculation that we can do to kind of dream about these systems a bit more. Let me tell you a bit more about the issue that existed kind of with these neutron star binary mergers. So if they would produce X-rays, and people at Columbia, for example, Brian Metzger and Fernandez here mentioned, have calculated that in better detail, then the X-ray radiation that could be produced, just if you consider the possible dissipation of all the available energy of the magnetic fields around these stars, is actually not high enough to be seen here on Earth. So that's a problem. That's a little crisis. So is it ever going to be possible to see electromagnetic signals from these systems? And then you could think about two ways that could happen. One way could be that the estimate you use to calculate this limit of available energy might not be accurate. Maybe you have more energy available by some other dissipative process, or maybe you would have alternative radiation mechanisms like coherent radio emission. I will talk more about what coherent actually means in a bit. That could, for example, generate fast radio bursts, and by a totally different channel and wavelength then pinpoint these systems. The difference between these processes, incoherent and coherent, from the plasma side is illustrated on this slide. And this slide we will go back to again and again as I also talk about different processes. So the incoherent one is the dominant one you also learn in your lectures. So if you have a Compton process, for example, inverse Compton process, everything where you have an ensemble of particles and you have interactions between particles with other particles or photons that then promote one single photon to a higher energy state. And this can happen, of course, again and again and again, but you're limited by the amount of particles and the energy of the particles that you have. I know many people here in the room study such processes, and then it becomes the question of how you re-energize your ensemble to keep pumping your photons into higher energies. So this is this classical incoherent emission process, how I call it here. The coherent emission relies on additional interactions in your plasma. That could be an instability. We know reconnection is such an instability. Several turbulence scenarios or other instabilities could happen. And then you actually have an interaction between your plasma ensemble, your N particles, and your interactions between them. So you have a much higher availability of interacting states, and these can pump much higher energy into this radiation. So radio astronomers measure this in something called the brightness temperature, which is just kind of an estimate of the temperature that some radiation might have. And the coherent emission is known for having very high brightness temperatures. And for FRBs, this is certainly true. One coherent emission process that I want to focus on throughout this talk that has been recently become very popular. So it's also riding this wave. What's happening here is that we think about a fast magnetosonic wave being injected into into plasma with a strong magnetic field somewhere. And as this fast magnetosonic wave propagates, it's kind of like an electromagnetic wave. It is not really affected by the direction of the magnetic field, so it can cross field lines. But as it expands and the wavefront becomes larger, the amplitude of this wave, of course, has to decrease with the power of the radius in order to conserve your energy. And then if you compare this amplitude of the wave with the background magnetic field, it can actually become the amplitude can become a significant fraction of this background magnetic field. So you can run into a nonlinearity of this wave. And this is especially interesting in the case where the magnetic field of your wave is not aligned with the background magnetic field, because then just everything adds up, but it actually points into the opposite direction or at an angle to the background magnetic field. So that's the case on the right here. And in such a case, what can happen is if you calculate the total magnetic field, so the background magnetic field plus the wave magnetic field, and compare it to the total electric field, which is only the wave electric field, then as your background magnetic field decreases, you can run into a situation where your total magnetic field and your total electric field in the system actually are comparable. And this is a situation that's actually not like permitted in ideal MHD, for example, that you have an electric field larger than the magnetic field, and you have to expect some dissipation to close this issue for you. And it's been shown by predominantly Andrei Belobrodov at Columbia in the past years in a beautiful theoretical derivation, actually, that's very worthwhile. What happens to such waves? And he shows that while they propagate, so on top of here, you see a wave. The positive part here is where the field of the wave is aligned with the background magnetic field. In the bottom, it's anti-aligned. And you see that when you run into this electric dominance, it just shaves off parts of the wave, and it translates this shaving off into acceleration of plasma, which then becomes a shock. This has also been shown kinetically recently by my good friend Arnaud van Tighem in France. They actually ran beautiful PIC simulations of such electric zones in then monster shocks, as they've been coined, and they've identified these kinetic instabilities here that also are responsible for the emission of waves in that process. So in this kind of context of coherent generation of emission, I want to go back to this binary system. And Andre and I, we thought about a very, it's a toy problem where we set up two rotating spheres. So we're in kind of the co-rotation frame of the binary. And we gave them dipole magnetic fields. And then we let them rotate against each other and see what happens to their magnetospheres. We also incline one of them at times, but we start with this very kind of basic setup of two aligned dipoles put on conducting spheres that we let rotate against each other with several simplifications, as I mentioned. And then we used something called force-free electrodynamics, which is a limit of magnetohydrodynamics, to simulate this system. So force-free electrodynamics is a bit tricky, as people in the room will know. You neglect all the influence of plasma pressure and inertia, and you pretty much evolve Maxwell's equations with a current closure and some extra conditions. And what that gives you is a great way to model large-scale dynamics of magnetic fields. It's not a great way to model particle acceleration or dissipation, but we use it commonly to just identify regions where dissipation could happen, or trace waves that are generated in such plasmas. And these fast magnetosonic waves that we're interested in are actually captured in this limit. And therefore, we chose it to just efficiently study such a large 3D setup of two rotating spheres. It has actually been much more interesting than we thought initially, because we didn't just end up studying kind of this nonlinear wave generation, but we kind of got hooked on just the magnetospheric topology of such interacting binaries. So I will play a movie here, which is our own educational movie on this. You see the two binary stars here. They will rotate in the same direction, so the field lines will move against each other in the interaction region. And then we also include 3 field lines on the blue star. They are just seated at different angles. This field line is actually seated at the pole, so you see the whole magnetosphere is kind of tilted to your left because of the compression. And yeah, so the color is for the field aligned current. I don't know if I mentioned. So if I play this movie, sorry, it's to load a bit, then you actually see the pulsar current sheets that you know from isolated pulsar simulations in both halves of this magnetosphere. But you also see this additional current layer between the stars in the interaction layer. So this is actually a place where you see some currents. It's a surface. You also see waves moving out on this surface. We'll look further into the generation of these waves in just a minute. And you kind of see this very interesting, maybe it's obvious to, but it wasn't obvious to us, behavior of field lines where you have a field line opened up on the current sheet of the pulsar, and then it experiences this kind of compression when it tries to push against the interaction region, and it reconnects, and then it has to open up again, this large-scale motion, and it does so over and over again. So that's just very, I think, instructional on understanding how the magnetic topology of these binary systems could behave as they orbit each other. So this is a great point to ask questions if you have any questions about this simulation setup or anything that I just said while this movie plays. If not, then I will continue to zoom in on the interaction region. So Andre was fascinated with this owl whenever I showed him movies of this, because it looks very similar to an owl if you actually check the charge density that you have between these two stars. So charge density is allowed in force-free electrodynamics. Plasma density you don't have. But in the charge density, actually, if you look at that, you can see something like Kevin Helmholtz vortices develop here. And what happens is that you have a shear layer that is created by these field lines that move against each other. And at this shear layer, the Kelvin-Helmholtz instability will generate some drag. So if I play this movie, you see on the left the field lines rotating against each other in the interaction layer, and you see this vortices in the charge density happen here. You can also look at the velocities, that's here, and the dots are kind of the field lines. And if you look very closely and kind of squint your eyes, you see how there's actually a drag that slows down the rotation of these field lines. And the thing is that after they've been slowed down a bit, they are released in a slingshot-like motion from this layer. And that's very interesting because in this slingshot-like motion, they introduce compressive waves. And these compressive waves could then be these fast magnetosonic waves that we're interested in for the nonlinearity arguments that I initially made. We studied the energetics of this, just to come back to my initial question of like, is the dissipation mechanism maybe a bit different? So on the left, you see a diagram where in the middle panel, we just measure the Poynting flux at certain distances from the star. And compare this to the Poynting flux expected in the single rotating pulsar. And we see some enhancement that is also explained by the compression of the magnetic fields due to the magnetospheres pushing against each other. So in the paper by Itzel that I initially mentioned, this is discussed very nicely, how your compression of a magnetosphere in a cavity can actually increase the energetic output. And then we have two additional panels on top and on the bottom. On the bottom is the energy we measure going into the interaction layer with the Kelvin-Helmholtz vortices. So we see that about 40% of the energy that's going into the Poynting flux is also going into the interaction layer and being dissipated there. So this is interesting because it would be an additional channel of dissipation that would not be accounted for in simplistic models of how much energy is available. For shadow, it doesn't do much to the estimate. Like, it still doesn't give you enough energy to see X-rays far away, but it's an additional contribution that has not generally been accounted for. On the top, you see the variation of Poynting flux against the average Poynting flux. So if you average your electric and magnetic fields because you reach kind of a steady state without inclinations, and then look at the deviations of Poynting flux from that, you get the top panel. And if we kind of are generous, then we can suspect that this might be related to actually outgoing fast magnetosonic waves that are created by these slingshot motions. And if we then are conservative, then we can kind of estimate that probably around 5% of the outgoing energy is carried by fast magnetosonic waves into the wind. And our point is then, if these waves would be strong enough, then that they could be available for these shock-mediated FRB models due to the electric zones that develop. Last movie on that looks at the electric field compared to the magnetic field strength. So the red color here, E divided by B, is larger than 90% or 0.9. And on the bottom, we just look at generally an outline of E divided by B at the bottom of this cube. So if we play this during the interaction, you see this abundant action of kind of waves in the interaction layer. But you also on the bottom see kind of is almost looking like water waves that just propagate spherically outwards. And this resemblance of water waves, though it's very hard to actually do the mode decomposition in such a dynamic environment, they are a very good indicator of that there's actually some fast magnetosonic waves being generated and then spherically propagating outwards. So as you see, some of these waves are pretty strong, especially in the interaction region. They are not generally very strong. And that's kind of an issue because they would need to become nonlinear before they reach the wind zone in order to generate these monster shocks. So we do have the conclusion that yes, we generate such waves, but also they are not always amenable to actually create fast radio bursts due to this mechanism. So some more detailed considerations have to be done here. We looked at different inclinations which can get a bit more energy into these waves. But in general, I think it has to be thought about a bit more in order to give limits on the actual FRB generation in these systems. Okay, another time for question on the binaries. So the next part will look more into single stars, magnetars. So magnetars are a bit different than pulsars in several ways. They're usually much stronger magnetic fields by 2 orders, 3 orders of magnitude. They have somewhat slower spins. And their spin down is extremely rapid. So they are the top right of the PP dot diagram, which I'll show you in a bit. While pulsars are these steady emitters over many periods, magnetars are not necessarily such steady emitters. They have quiescent episodes, they have bursting episodes. Most of the magnetars actually have been discovered in bursting episodes. And as I'll argue, it's not too clear where actually plasma comes from around these magnetars. So that's very interesting for somebody who's interested in plasma around compact objects. And it's kind of the big thing we have going on at the moment, that we actually want to figure out where such plasma is from. So this is a PP dot diagram. We've looked at the big pulsar population in the middle, and the binary somewhere in there. Magnetars are on the top right, so with very strong magnetic fields, rapid spin down, and slow rotations. They have a rich set of X-ray activity, most notably giant flares or other bursting activities. Magnetar bursts are usually rapid in rise time, and then they decay over some time. There's a lot to be said. It can actually be a separate talk of just the burst morphology and how this tail can extend over months to years if you look closely. And you actually see like the magnetar rotation imprinted on here, but also some other frequencies. So there's a whole lot of interesting physics that is in there. And of course, at least one or several FRBs, as you've read in the additional material, have been associated to magnetar origins. And then, of course, it's a question for us around the magnetar, what could make such radio signals? And some of the details of that I will go to in the next slides. I quickly want to point out some of our work on X-ray bursts. So this is going into the incoherent emission side. Other people looked at that as well, like Kyle Parfrey, but one thing we do a lot, and that's kind of what I want to use this slide to for introduction, is that because we don't, I mean, people like Yuri and Ashley who are working on that hopefully will give us a bit more insight on that in the future. But what we did so far was we kind of dream up motions of magnetic fields on the stellar boundary. And then we put in different of these prescriptions into our codes and see what the magnetospheric response to that is. And here, for example, we put in a motion that looks like this. It's a ring-like, fault-like movement of the crust. And if you let this movement happen on slow timescales and see how the magnetosphere reacts, this is a 2D axisymmetric simulation, then you actually see that you have these eruptive states where you create a lot of reconnection and you expel a plasma blob, your field lines extend for some time, and at the end of the movie, if we let to play it again, you actually get this kind of magnetic field structure, what solar physics people always reminds of kind of coronal mass ejections. And here you don't have mass in this simulation, but at least you have like an ejection of magnetic energy. And so we did calculate that all of these eruptions that happen so symmetrically can actually power the most energetic flares seen from magnetars. We've then moved on to where we don't actually perturb the entire sphere of the star, but only a hotspot-like element of it. So imagine a little circle like this one, moving in one direction slowly on the magnetar, twisting a bundle of flux tube, a bundle of magnetic field lines. And if we do that slowly, then you can again actually generate these large-scale eruptions. So here you see that the magnetosphere has opened up. In a cut through that, you might see somewhat similar topology, but you see this very active reconnecting episodes and dissipation episodes. And in the right panel here, you actually see the Poynting flux being ejected from this very simulation. So you see that after such an eruption, there's a lot of energy being expelled into the extended magnetosphere. And if you look at this most recent paper that I put into the reading, where the people actually see a lot of these X-ray bursts happening again and again, actually what observations start to infer is that there has to be like kind of an ongoing mass transfer into the magnetosphere. And I think some of these more reconnection-like events could actually be responsible for such transfer. So that's interesting to kind of revisit in this context. If we go more into the FRB part of that, then we are not so interested in the kind of incoherent radiation mechanisms where you just have a lot of energy dissipated, for example, in a reconnection event, but we're more interested in instabilities and these waves again that we talked about before. And we actually saw in the same simulation than the one I just showed you, where we have a bundle of magnetic field lines that we twist, that if we select a slightly different shape of the bundle, for example, we put it closer to the equator so that the magnetic confinement is stronger, or we twist it in a slightly different way, then we don't get big eruptions. We just get kink instabilities. And these dissipate much less energy, so they might not generate so much of the bursts that you see. But what these instabilities nevertheless do is they, again, through a compressive dynamics in the inner magnetosphere, they seed fast magnetosonic waves. So this is a bit of a messy plot because this simulation was never thought to kind of study the large-scale magnetosphere cleanly and look for these waves. But what we again see is that we have these water wave-like patterns emerging here from just a kink instability that didn't dissipate much energy. And then at probably around 100 stellar radii or so, even very low amplitude fast magnetosonic waves can develop these nonlinear zones where your electric field becomes comparable to the magnetic field. And that then again could mean that your shock mechanism, monster shock mechanism, could work there. So this is currently being followed up actually in MHD simulations to overcome the limit of force-free prescriptions that we chose here. And I think in the next months or so, it's not in my group, but other groups will do a very good job in actually explaining that phenomenon much better. Then so it's become like a game for us to just change the surface motion and see what happens and think about different physics. And here we have a slightly different twist that we install on the surface. And this time we don't do it slowly, but we do it kind of in a periodically oscillating way. And if we add such a perturbation and oscillate it, then we can actually inject alpha waves into the magnetosphere. So alpha waves you see on the left here in the B phi component, because it's an axisymmetric setup, you can do this nice decomposition. And fast magnetosonic waves you see on the right. And in my group and also other groups, we've recently shown that you can actually inject fast magnetosonic waves just by alpha waves kind of interacting with the curved magnetic field lines of such a magnetar. And again, because then you have these fast magnetosonic waves propagating on a decaying magnetic field, you can develop these electric zones quite naturally during the propagation of the wave. So again, you vary by injection of a very small amplitude wave on the magnetar surface, you can generate some radiatively interesting dynamics further out. This can be analyzed quite a bit more. So actually, this is the outline of the outgoing fast magnetosonic wave train. And you see that the first part of this actually has a high frequency component, which is the only part that actually has the frequency of the ingoing alpha wave imprinted on it. Then at later times, you just have alpha waves bouncing around in the inner magnetosphere, and every time they create some long wavelength waves. And here you actually see the shaving that happened due to the E larger than B constraint. Unfortunately, in this force-free electrodynamics limit, we don't have other plasma properties, but this is something that MHD would definitely give us and will give in future simulations. The last kind of point I want to make, and then I can speed it up a bit, is that all these environments that I've shown you are pretty magnetically active. So it's very easy to think that you could have aphanic perturbations being around these environments, also close by to the magnetar. So this has been a very simple perturbation, and alpha waves have become extremely sheared, but they definitely have some leftover perturbations going around in the inner magnetosphere. And that actually becomes, I will skip this a bit, becomes interesting for a question in the additional reading that I pointed out, which is related to the escape of fast radio bursts from the inner magnetosphere, for example, of a magnetar. So there's been this long ongoing discussion, which probably people in the audience are familiar with, especially between theorists. So long story short, some people think fast radio bursts can be generated in the inner magnetosphere and then propagate outwards. Other research actually shows that this might not be the case due to several resonances or absorptions. Then, of course, counter arguments are that it might be line of sight dependence. Yeah, it's a mess. And the reading I outlined by Kenzie Nimmo and her collaborators actually tries to use scintillation studies of fast radio bursts to pinpoint the emission region a bit more, or at least the size of the emission region. This paper is really interesting to read. There are caveats to it. There might be large error bars to it. That might not be the final story. The conclusion that the emission region is only like a few hundred meters in diameter. But it's a very nice way, I think, that observations are trying to actually provide data for this long ongoing discussion that we have. And what I will talk about now is also about this question of if fast radio bursts could escape from the inner magnetosphere, but looking at it from another different angle. So this has originally also been proposed by Yuri Lubarsky and his group in Israel. What could happen is that if you have a radio-like wave created in the inner parts of the magnetosphere, this wave might encounter some of these aphanic perturbations that I was talking about just before. Aphanic perturbations that are left over from other magnetic activity, from other waves just being emitted. They basically can be around. So you could have an escaping fast wave, and you could have abundant alpha waves propagating along magnetic field lines and eventually encountering these fast magnetosonic waves. And then we have Siddhant, who's a student at the University of Maryland, who used our code to actually look at 3D simulations of what could happen in such an interaction. And he started with a monochromatic fast magnetosonic wave here, and he put in a spectrum of alpha waves in the back. It's still a bit simplified, of course, because kind of keeps everything constrained to a box, but it's a nice first step, and he continued to study this. And what he did is he let that evolve in time, and he looked at the spectrum of these waves. And here you just see an outline of the magnetic energy, and you see that in time, actually, your wave pattern starts looking very different. You don't see the clear monochromatic waves anymore. So it's definitely worth looking at the spectrum of these waves and what happens. And what Siddhant finds is that your initial fast magnetosonic waves the blue line here, actually, due to the nonlinear interaction that you also know, of course, from turbulence, decays in energy and power, and it also broadens substantially. So your energy in your original frequency might become much less over time, and you also might pump energy into other frequency bands very easily. And at the same time, you have this resonant generation of alpha modes that could then propagate further to the magnetosphere that we also see at that time. So your initial flat spectrum of alpha waves, which we see here, actually get some additional modes due to these interactions. So this is a very fundamental and interesting, I think, way to look at this. And Sedan found that actually the alpha and fast magnetosonic wave energy, even though initially vastly different, equilibrates in these setups. Your fast magnetosonic wave energy becomes much less. And he will give in a paper that we're just reviewing several estimates of what you could expect actually from realistic estimates of how long the interaction time between these waves would be in a magnetosphere. And the conclusion is that definitely in some cases, this can also make it hard for high frequency fast magnetosonic waves to escape the inner magnetosphere. And we look forward to, of course, discussing this with everybody interested in this kind of theory puzzle that's been around. Okay. I will go to the final part of this talk, which I will just hint. So this is something that has cost me very many hours in the past 2 years or so. So we're actually trying to model what happens not to the bursty activity of these magnetars, but to the persistent emission. So what happens after the burst when you have a persistent X-ray spectrum being emitted from these objects that can last over many years. So obviously after your burst, somehow plasma has to be around in the magnetosphere. But to be honest, nobody really knows how it got there and what keeps it there. There are some theoretical models, very elaborate also around, but in a like fully nonlinear description, it has never been done. And this is again an incoherent radiation process. So what we see in these X-ray spectra is a thermal component, which is on the left here. And then we consistently see this hardening component. And the transition of photons between the thermal and the hard component is what we want to actually study from first principles. There's a lot of actually interesting observational work going on. I just want to point out, I think XP just has some simulations post-burst where they can actually, not in this object, but in an object where your hardening starts earlier, like in the sensitivity range of XP, where they can look at the harder part of the spectrum and actually extract the polarization information of that. Not at all my expertise at the moment, but something I'm excited about to see and think about in the next month and years. The toy model, I think I need like 5 more minutes, then I'm done. The toy model that we have in mind is something like this, where we have a twist installed again, like different twist in the magnetosphere. And this twist actually will accelerate some particles from your surface. So it might be electrons, positrons. Protons will be harder to accelerate, but might also be important in that mix. And then these particles propagate along magnetic field lines. And at the same time, you have these thermal photons coming from the star that just propagate in a straight line. And then at some point in the magnetosphere, they might come to interact, to collide, and actually create, for example, pair production cascades or other relevant ways of igniting this circuit or this plasma flow in the magnetosphere. This is the slide I probably don't have to show all of you, but this is kind of the slide I toy around with behind like this theory. So you have a curl of the magnetic field, which comes from the twist. And you know then, by just Maxwell's equations, that you have to support this twisted magnetic field by a current. And at the same time, if you look at the current, you know that you have to support the current by charges of a certain number that flow with a certain velocity. So this is a balance of pretty much just two things, which is particle number and particle velocity of a species. But at the same time, like your kinetic physics of acceleration and your QED physics of deceleration and changing the particle number heavily affects both of these components, like your N and your V. So it's a very interesting puzzle to kind of ask what would be the balance in an equilibrium state and how would you get there. And this is what we do. We use for this one particle and cell simulations. So here we actually need all the plasma kinetics, we need the dissipation, and we need to add radiation to it. We use a new GPU accelerated code that we wrote, part of the reason why we're so slow in this project. But it's looking really good by now. And we do have, I'm skipping the radiative part, some simulations ready now. So again, here you see our favorite twist of the magnetosphere. And we start from a vacuum this time. So this is the particle density. You just see a bunch of particles close to the star, which are held by an atmosphere prescription. And then as we start twisting, you will see that there's a magnetic field installed, that you will get particles, you will get a current, and you will start to see accelerating electric fields that are pointed along the magnetic field. And this is what that looks like. So we install a twist, and after the twisting has stopped is when the interesting part for us starts. So then we want to study this equilibrium. And it's remarkable, I skipped that, that in this simulation, we have the full prescription of resonant inverse Compton scattering implemented. That means we check for every lepton here if by the thermal photons in the background you can excite the first Landau level, and if so, then we let it scatter and actually do this radiative reaction that we think could happen for fast particles in the magnetosphere. And I will close with that because I'm running out of time. What we also have in this simulation, and that will be the remarkable addition, is that we will actually have photons that we can track. So we have upscattered photons. Everything in color here is something that has got a higher energy than the thermal photons that are around everywhere else. And we will be able to extract a spectrum from that and actually relate these first principle setups to actual observations. Just saying there's still some final things we need to understand. So here you see a bunch of particles that have just stopped along the equator, but it's not a current sheet. Like you don't see field lines opening up. What happens here is that the radiative drag just makes particles slow down very efficiently, and we're just calculating the impact of this for the different kind of regions you have in these magnetospheres. And well, we could go on how challenging this is for simulations and such, but that will also be an output of this current project that we will kind of describe all the different zones you have to expect in such a magnetosphere and how they are radiatively important. I will skip a bunch of stuff. We can go back to that if it's interested, and just leave you with my summary slide. This whole catalog that I presented here, we pretty much try to identify regions of incoherent radiative plasma processes where you dissipate energy and give it to photons. And we also try to consistently model coherent plasma processes, or at least identify where they could happen. Magnetospheric instability is very important, both for dissipation and other radiative mechanisms. And shortest part in the talk, but most exciting thing to come up, is that we are doing really first principle simulations of the magnetosphere, where I think, will give a lot of first fundamental understanding of the physics in there, but also implication for radiative modeling, like what plasma velocities should you use for your XP pipelines. This should be an answer that comes out of exactly these considerations, and hopefully sometime later this year. I've been saying that for 2 years or 3. we'll have something for you there. I look forward to discussing that more. Thank you.
Thank you. Thank you very much. That was a great summary. Thanks. Questions? Yuri, please go ahead.
Great talk, Jens. I really enjoyed every single part of it. I'm curious about the force-free simulations. I mean, force-free formalism doesn't, as far as I know, have a good prescription for how you deal with current sheets and dissipate, regions where dissipation happens. And yet, in your model of interacting magnetospheres, this is precisely where interesting things happen. So can you comment on that? How robust do you think that is? Can this be checked using other methods? And more generally, what is the way forward for force-free simulations to model this type of regions?
Yeah, I think that's a wonderful question. And yeah, so there are different, also in the literature, if you go back, because this has also been used, for example, to model black holes. And there are different approaches to that. The most drastic approach is to say whenever you have a violation of force-free, for example, E larger than B, then your simulation is unphysical, which is probably the correct answer. And you should be very careful in using it. So what we try to be careful with here is that we either keep these violations constrained to a current sheet in a controlled way, or make sure that they are transient. And even if we do that, then the statements we do about variability and dissipation rates might still be off, just as you say. What has to be done then is that they have to be checked with at least MHD simulations, like fully MHD or resistive MHD simulations in the case of the binary. PIC simulation is not that interesting there because probably it's actually collisional plasma. People are doing that right now. And actually it's reassuring that they also found these Kelvin-Helmholtz vortices if they run this in an MHD simulation. I think the timescales of growth and variability and dissipation can be slightly different, but it's reassuring that they are still there. So yeah, all this is very important to have in mind. You're right. In general, for force-free simulations, I don't know what's the way forward. I try to use it more as an inspiration to understand where to look next and explain possible, other processes more completely.
Do you think there is a room for implementing different sorts of Ohm's law as people have tried, like strong field electrodynamics or things like this, where you have some different prescription?
Mm-hmm.
I know this is not perfect, but I'm just curious whether there is any hope for these theories to converge to something.
Yeah, so there has been like some, and I have indulged myself in some ways where just the currents are changed by a different Ohm's law, but you pretty much keep everything the same. And this is a bit hacky because you just prescribe your dissipation rates how you want them. You can make them slower, and then it might look more like ideal MHD, but that might still not be correct. What's more promising, I feel, is so in two different branches of the community, there's been some perturbative approaches where you try to bridge this region between force-free limit and MHD by actually capturing some of the dynamics at the second order. And I think that can be a promising way forward out of this. Not so much I give you a sigma and you give me a time scale that matches the sigma kind of argument.
Thank you.
So I had a quick question. You showed one of the, I think it was a Swift observation, X-rays, spectral energy distribution.
Yes.
I was just curious. So, I mean, you're working with observation people for testing, and especially the IXPE results, right? So, what are the sort of things? I mean, you mentioned that this is coming down the road, and what can we test observationally?
Yeah. So I wish I was having more bandwidth to actually understand and work with observers. So I should do that more. I think it's fair to say, and it's also not meant in a, it's not meant in any, yeah, don't misunderstand me. So a lot of the models behind the interpretation pipelines of these observations are based on very simple assumptions of what the magnetosphere here looks like. Dipolar, very simple assumptions of the plasma velocity, very simple assumptions on the multiplicities and decomposition on different field lines. And I mean, this is something that I think we can provide from these models. If that has a big effect on the interpretation of observations, I'm not actually sure about, but for sure, we can become more realistic in it. So this is my big hope for the XP part, and it's so there should be like a lot more feedback. It's very interesting if you think about what is the polarization state of these thermal photons, like when they just come out of the atmosphere. And if I use a different polarization state as the seeds in my simulations, will it change the equilibrium in the end, or the kind of polarization that you get out of the photons on the other side that would then be here? And does that match the XP observations that will be coming in? So I think in this kind of realm, there's a lot of collaboration and exchange that can happen, and I hope we can make that work as a community.
Yeah, yeah, it's very interesting. Thank you. Any other questions?
Maybe observationally, are there any cyclotron resonant lines forming in your simulations? Sort of, can you get, besides polarization, can you get a spectral signature?
Yeah,
that
that's
way?
also a very good question. I never thought about the cyclotron resonance so far in my simulation, but they're very important for the observational part of this. And I believe also for, yeah, I haven't thought much about it, but it's something on the list.
Cool. And maybe because Rashmi and I are sort of into MEV instruments, do you have any thoughts about whether it's important to have an MEV observation? Because the spectrum's unbroken and very hard, and the peak is somewhere. MEV, does that impose any restrictions on the plasma physics?
I
And,
think, yeah. Sorry, I interrupted you.
No. I was going on. And then in the old, very ancient days, people modeled everything as some saturated pair fireball, which gets MEV. And are you going to do that? Are you going to end up in that regime, or is your stuff occurring in a different place?
Yeah, also very good and exciting question, especially also about the high energy part of the spectrum. So observations trace this actually, and it's clear, not this one, but yeah, I should prepare one slide of that. So there are different spectra that actually, where you don't see them extend beyond a certain range, but it's completely unclear where the kind of cutoff of this hardening happens for magnetars. So I think COSY is coming up as a mission in that spectral range, and that will be very interesting to actually check, like, until when is this hardening going on? And that should be an important information, I think, on the plasma in some way, probably involving more processes than we currently have in our in these first principle models. But I think that can be very informative indeed on the kind of plasma we have there.
Thanks. Yeah.
Yeah, so COSY would be great. I've just seen yesterday a talk with I should have this slide where you see this large, white spot in the spectrum where you don't know what's going on, and that to see that filled will be good.
If there are no other questions. I had another question. So another thing that can go wrong is, I guess, the charge density is whatever it needs to be to make the force free work. Do you get gaps where in principle, you can't satisfy the charge? Have you
Yes.
checked that?
Yeah, that's a good question. So in the force free simulations, yeah, it's mostly well behaved in the magnetar simulations I showed. In the binary cases, as you mentioned, that's a bit more involved, that we have to just to make sure that they don't affect the relevant dynamics. But you're saying gaps, I actually want to point out some of the interesting parts or some of the things that are relevant for this magnetar thing. So actually, this is a kind of model of a one-dimensional model of a dipolar field line. So this one. So here you see electrons and positrons from the surface. Positrons will not radiatively interact. I fake them as ions. Don't worry about them. And then you have actually secondary pairs here. And then there will be the radiation along this field line is kind of like in a dipole. Like it will be strong close to the star, which is here and here. And it will really make the plasma almost stop down at the equator. And it's a huge question how the gap structure close to the star looks like, and how it will be maintained, because you see the gap is actually accelerating particles. It's immediately dragged down by the drag. So not even in force free, but even in peak, it's like our big challenge to make sure that the acceleration here is so well resolved that the gap actually makes sense. So this is the gap structure of the magnetar circuit is kind of the reason why it's taking so long, because we want to be really, really sure that we don't sell gaps that come from insufficient resolution or other things. We're getting there also with these 1D models, actually, rather than, even though we're excited about the shiny simulations, but they will be very helpful in understanding this gap structure. And in force free, unfortunately, because you don't have the different species in plasma, all this is fake, I have to say. It's not suitable to explain this.
Yeah. So this is a PIC simulation here?
Yes. Yeah, this is a 1D PIC simulation. It's a highly toy modelized. So the magnetic field is just along the X direction. It's constant magnetic field. In a dipole, it would not be constant. But the radiation kernel of the resonant inverse Compton scattering that needs the magnetic field and photon direction as an input kind of sees a different magnetic field just to fake the cross section along this field line. And then you can kind of get an idea what the flow would be like and where pair creation would happen, and how your gaps would form. And it's interesting. So this is what the particles do. And this is what the density would look like, and pair creation rate and multiplicity, and the electric fields, which is the gap structure. And then if I play that, then you see this large density being accumulated here because of the slowdown. And here you have the pair creation and the multiplicity that is required to screen the large-scale electric field. So it seems to be it's amazing, and it's my own limitation because it's such a simple problem. Like you start from a vacuum and add some drag to it and some pair production, and then you ask what's the equilibrium state. And it's actually not straightforward. We're getting there, but it took us a lot of iterations. And you actually see here, sorry, I'm going on because it's so fascinating. And you see here like this plateau. That's actually also fake. We put in some like pair annihilation artificially here, because otherwise your density just becomes so large that your skin depth is not resolved anymore, and then everything breaks. So there are like tricks we have to do on that as well, but we'll get there. I'm confident.
Oh, wow. This is pretty amazing. Okay. Because I thought about this a long time ago. Yep.
Yeah.
Is there one issue like PIC codes and radiation is, in principle, the radiation scale length can be much larger, like the photon could go many skin depths. How do you handle that or think about handling that? that's the case here.
Yeah,
What
it's
could
a
be the case?
yeah, it's also a wonderful question. So yeah, radiation gives you just another scale to worry about, and that's not actually straightforward. So here, to simplify that, we do not worry about mean free path of created photons, so everything instantaneously pair produces.
Okay.
But in the simulation we envision, especially in the 2D one, that is not sufficient, because that's actually what brings you the worth of putting this like full prescription in there, because then a photon produced by scattering on one field line can actually carry a pair to another field line and give you a multiplicity there that might actually be very relevant to sustain this current. So yeah, we have to rescale it in a way that is realistic. We're still working on the details of that.
Cool. Well, in the old days, also, you could have the photons crossing field lines and exciting electrons into Landau levels and other lines, so you spread things around and you're not locked.
Exactly. Yeah. So this is actually an important part of why the 1D setup will not be sufficient, or also why so first attempts to do that in global simulations was actually with like an ad hoc prescription as well. So you pair produce whenever your particles reach a certain velocity instantaneously. But what you're missing there is this transport of pairs to other field lines, and multiplicity in the extended magnetosphere can become very relevant for these models of the plasma circuit. So yeah, it seems a simple question, but then it blows up into your face.
Yeah, definitely. Okay. All right, thanks. I've been talking too much. Any other questions?
Yeah, I think we're losing people now. So that was
Sorry.
really excellent. As Yuri said, every bit of it was really excellent.
Yep. Very
Thank
good.
you for
I'm
listening
really
to
glad
it.
that we recorded it, and we'll keep watching it. There's a lot to absorb. So
Thank you.
please send us the slides as well, and
I will upload them for you.
And I hope you can continue to join. We have some other IXP talks coming up as well.
Yes, I've seen. I'm very interested in this series. It's really a great series you put together. Thank you so much.
Yeah, great. Thank you. And
Thanks again.
thank you everyone.
Have a great day. Bye-bye.
Bye-bye.